All right. So last time, we proved this universal property of sheafification that said, for every morphism between a pre-sheaf and the forgetting of some other sheaf, there was this very special map theta that we defined, which goes between the forgetting of the sheafification of F, and there'll be a unique map F tilde, which makes this diagram commute. So part of that was this claim I said that we could write theta actually, despite the fact that I left some details out. Theta actually defines a natural transformation between the identity and the composition of these functors. And another way to see this is that actually we have a bijection. So this is homomorphisms in the category of pre-sheaves on X from F to the forgetting of G. And this, I claim, is in one-to-one correspondence with homomorphisms in the category of sheaves, where instead we have here the sheafification, and here's G, right? So one direction of this bijection, well, one direction is easy, right? If you start at this set, we just defined all homomorphisms of sheaves to be homomorphisms of pre-sheaves. So well, but that's not, we don't have the F plus over here, right? So that's kind of the problem. But here's how the map works, right? Suppose that we had an F over here. Well, that's just this F over here, right? And in particular, then we get F tilde, right? We get an F tilde. And we get a unique such F tilde, by the way. So this process is injective. And in particular, so the way it's written over here, of course, I've written this as a more F tilde as a morphism of pre-sheaves because it's the forgetting, but of course a morphism of pre-sheaves or a morphism of sheaves is just a morphism of the underlying pre-sheaf. So actually, this really does give us a morphism from F plus to G. And so the claim is that this, in fact, is all possible, that this is a bijective correspondence. Okay, I'm not quite going to get into all the details of that proof because today we're going to venture further back. We've really got our hands dirty in the last couple of videos with sheaves. I'm going to venture back into the world of abstract category theory because part of the idea is sort of using this course as a way to get introduced to the ideas of categories and see them in, say, this geometric context of sheaves. So what we've defined here is a particular pair of what we would call adjoint functors. So in this case, we would say that sheafification is, and I always put the turnstile the wrong way, except maybe I don't now, but we would say it's left adjoint, because it's the thing that you put on the left slot in the Hom set, to the forgetful functor. So 4 is right adjoint to sheafification, or sheafification is left adjoint to the forgetful functor. Okay. Why does that matter? Well, first off, this is a thing that comes up many times, and there's sort of some general theorems we can prove about adjoint functors that allow us to do some stuff. So like I quoted Hartshorne in a recent video. If you look at the exercises there, there's some exercises that are made pretty easy once you understand some things about limits and adjoints of functors, which we're going to get to. So, another reason is generally speaking, I mentioned there's this, between two general categories, right? I can have a pair of functors. Well, either these functors can be, they could be like bang on equal to the identities in each case. And, I sort of argued that maybe that's a bit too strong. So then I said, well, maybe instead of having them just straight up equal, maybe they're at least isomorphic as functors, which is to say there's some natural transformations between these things. Oh, X, that should be a C. Right. But then sometimes, there's you could imagine that let's say that we don't even have an isomorphism of categories, right? So maybe these arrows aren't isomorphisms. But we could have, so I'm going to call this one epsilon. And I'm actually going to swap the direction of the other one for reasons that may or may not be so clear in a moment. And I'm going to call this eta. And so maybe we have natural transformations, but those natural transformations aren't even isomorphisms, but they're still going to satisfy some other sort of nice kind of property. So by the way, eta is called the unit. Epsilon is called a co-unit. I'm going to turn the messaging on my phone down so it doesn't interrupt me again. And so what? Oh yeah. Well, we're going to, that's not all. So these are natural transformations. It's not going to be any natural transformations. They are going to satisfy a very specific properties that are kind of dual to each other. So one of them says that for all choices of a map, F, do I want to use F? Yeah, F from X to GY. So for all objects, X and Y, by the way, so I guess I should say, X for all choices of X here and all choices of Y here. That, I've put this in the wrong place now. Yeah, so for all F, I don't know why I just changed the color. That is the right thing, that's what there is a unique H going from FX, I guess I should make that a scripty thing, to Y, such that the following diagram commutes. So X to GFX. So remember, eta is a natural transformation between these two functors. So that says that eta gives me a map for each x. If I plug in x to both of these, which what I've done here, I should get some map eta sub x between these, right? And what's going to be true, well, I also have this map f that I chose that just goes into gy, right? And I chose, so H is a map. In fact, it's the unique map that does the following thing. Well, it goes from Fx to Y. So in particular, GH goes from GFX. I think I'm just getting lazy on making the script notation. That's fine. To GY, right? So that's going to fit in this diagram here. Okay, so that is something that tells us a thing about the unit, and you might be like, "Oh, I, who cares? Big whoop." Well, remember I told you to hang on to that example where we had a morphism going from the identity to composite of functors, right? So this theta that we defined last time, going from a pre-sheaf, you know, well. Uh, a pre-sheaf to the forgetting of the sheafification of that pre-sheaf, this is actually an example of a unit of an adjunction. So that's where it actually comes from. But we also need something on the co-unit. That needs to do something special as well. What is the diagram for the co-unit? Well, it's basically, of course, I had to make some notes for myself because it's getting all twisted up, but it's essentially the dual thing, right? So for all h going from fxy, you've got a unique f going from x to gy, such that what? Well, I mean, we think about the commuting diagram we had here. It's going to be a very similar sort of thing. So we've got our map fx to y, and so that's our h. We have our gf y, and we have our, remember now, our co-unit of adjunction goes from f composed with g to the identity, right? And y is an object here, so I can plug it into both of those functors. And because it's a natural transformation, I should get a map between those. Sorry, this look more like a y. And then here, this is my map. Oh, geez, what have I done for it? Yes, this is f, the functor f applied to f. And so that diagram commutes as well. I guess I should have maybe put a swirly, but generally, if I write a diagram, I mean that diagram commutes, at least in the series. Okay. So that is one definition of an adjunction. But in particular, so remember, I talked about just up here the universal property. Essentially, what I was explaining here is how the unit gives us a map from one of these sets to the other. And so, as you might expect, how does one get the inverse map? Well, that would be from the co-unit. So in general, the unit and co-unit, another equivalent way to package up the definition of a natural transformation is by saying that there's a homomorphism. So this is in the category D, F, X, Y, and this is in the category C, X, G, Y, that there's a bijection here. Well, that's not quite it. There's got to be a little bit more. What is that little bit more? So, well, maybe I'm going to pause for a second to talk about some examples, more examples in a second. But you know, generally you should be suspicious, right? Oh, just a bijection, just a bijection. I mean, up here, the way we formulated it was that we had the existence of this unit and co-unit, right? So these things should be natural transformations of functors. And we've got a whole bunch of functors going on here, right? We have Hom-functors. I don't know to what extent I've explained that. So maybe I need to talk about Hom-functors a little bit. I'll do that in a moment. So maybe there should also be some more compatibility going on here, is what I'm trying to say. So I'll be more precise about that in a moment. In fact, I would even say painfully so. But with that in mind, let me talk about some more examples. So in general, right, what did we have? We had this process up above of sheafification, right? And forgetting. And this actually is part of a general mantra that in mathematics, free functors are normally left adjoint to forgetful functors. So what do I mean by that? Like, let's say some other context. Well, suppose we have a topological space, right? So X and tau, and that is just some topological space, right? Well, remember a topological space it's a pair, it's a set, right? And some collection of tau of subsets of the power set, which define a topology on X. Well, you could, and you know, in fact, we care about the category of topological spaces, where we have, you know, maps between the underlying sets that are continuous. But of course, we could just forget that we had topological spaces in the first place, right? And just consider the underlying sets. And if we did that, I mean, our continuous function would still be a continuous function, right? So we have essentially a forgetful functor from the category of topological spaces to the category of sets. Conversely, can we take a set and turn it into a topological space? Well, yeah, there's lots of ways to do it. Can we necessarily do that in a way that is functorial? Well, there's sort of two obvious stupid guesses, right? How do you put a topology on a set? So first off, there's, you know, given a set X, you can create the discrete topology, right? So that's the topology that just consists of X and the empty set. Or you could take the indiscrete topology in which you make every subset of X open. And in particular, well, I claim that that if you have that this is indeed functorial. So now if we just had some function of sets, any function of sets, I claim that if you do this with respect to both topologies, I claim that this function will be continuous in either case, right? So either we take the indiscrete topologies on both or the discrete topologies on both. So easier to see in the discrete topology case. Okay, so here's the part I forgot to look up before I did this. So I'm just going to say it's an extra exercise because I always forget. So here we have, this is forgetful functor and discrete and indiscrete. And so I claim that there's actually a three-way adjunction. So the forgetful functor is both, it's left adjoint to one of these and right adjoint to the other, and I mix up which one, but if you want to challenge, don't look it up and just think about what has to be true, right? So think about how, you know, think about if you had, well, if you had here, you know, topological spaces, or so, sorry, here you had sets, and here you had topological spaces, you know, and here you had to pick, say you had some particular set homomorphism, well then which two topologies, maybe I should have wrote this as Y sigma, right? So which topology do you put here that makes all of these functions continuous? And then by the same token, if you wanted to swap the directions, right? So you've got the forgetful over here. You know, what's the other topology you put on X to make, if you started with all functions here, continuous? Okay, that fell apart a little bit, but I'll let you guys look that up. So that's just more examples, but this happens time and time again, right? So generally, if you have some kind of category and you've got some objects, and you know that you can just forget that there ever was any structure, right? Well, then you should suspect that there's an adjoint functor lurking around that allows you to turn the underlying objects into that category. So another example, is groups and sets, right? So you can, again, you can forget that your group ever had a group structure and take the underlying set. The way that you go back is actually the construction of a free group on a set. So that also gives you a pair of adjoint functors. Okay, so let me come back to this thing up here and explain what I mean by the naturality condition. So I guess there's two things I need to tell you about functors on any category. So suppose that I have some category C. And suppose I take some object in C's, maybe I should say C naught for the class of objects. Then I'm going to get a functor from Hom from C into the category of sets. Well, technically, I don't want to talk about set theoretic issues, but let's call our category locally small, by which I mean I just assume that all of our Hom sets are, ZF, maybe C sets, right? So for instance, the category of topological spaces, right? Too big to be a set, but at least the collections of homomorphisms, right? Continuous maps between any two topological spaces, that's still going to be a set. Okay. And well, you can imagine that, what's it going to do? It's going to send an object Y to the set of homomorphisms from X to Y. And what is it going to do on morphisms? Well, suppose I have a morphism Y to Z, then I need to come up with a morphism from Hom X Y to Hom X Z. Well, I can just post compose with F, right? So if I had, right, given if I had some morphism in my category from X to Y, then because I have some, fixed map F, then the composition, right, this gives me a map from X to Z, which is where I wanted to go. So post composition. So here's something that should look familiar, by the way. So in category theory, we always expect things to have dual definitions. Suppose I had a functor into here. Well, that is not going to be a normal functor, but it is a contravariant functor, which goes from the opposite of our category into sets. In other words, if you remember, this is just a pre-sheaf, right? Not on a topological space, but an example or a more abstract example that we did see before earlier in the series. And so you could probably guess, I think, right from this is that if the map on morphisms was post-composition, then in this case it should be pre-composition, right? Well, yes. So of course, as you probably already guessed, Y is going to get sent to Y is going to get sent to the set of homomorphisms from X to Y. And okay, so if this is a functor, right? Suppose I had some F, right? In the, so here's some notation. So sometimes we might write our Hom sets like this. So, right? So you can read this as the same as Hom, but I'm saying that this is Hom in the opposite category, right? So suppose I had a homomorphism, right? If this is a functor, I need to tell you, given this homomorphism, I need to produce for you a homomorphism between the objects of the images, X, Z, right? But a homomorphism in C op, remember, that's just that category with all the arrows flipped. So that is really the same thing as a homomorphism from Z to Y, right? So I've got a homomorphism from Z to Y. And now I'm supposing that I had a homomorphism from X to Y down here, right? So X into Y. And uh, oh, I've made a mistake somewhere. Ah, yes, of course. Very, very foolish. Sorry. I applied the wrong Hom-functor. Maybe you caught that before I did at home and you were yelling at the screen. Right. Sorry. Yeah. Uh, so this should go right. So suppose I've got G over here. That is a map from Y into X. Well, what am I going to do? Well, I could just pre-compose with F, and that will give me a map from Z into X, which is what I wanted. So the map here will be pre-composition with F, just as we could have guessed. Okay. But kind of you already knew the second part, right? We've already talked about pre-sheaves as functors. So this, right? This is just it's another pre-sheaf. Surprise, surprise, it's all sheaves. Okay. And so now I have no idea how long this video is gonna be, but now I want to go back and really talk about this naturality condition. So how do we talk about that? Well, let me rewrite it down here. So Hom, this is my category D. I've got f of x, y, and I've got morphisms here and x. Yeah. Okay. So in order for this to be somehow natural, right, to respect the functorial nature, I should be able to make different choices uh, of morphisms. So in particular, what I'm going to need here is and you'll see why maybe I chose this in a second. So suppose I had a map from X prime to X, so that map's going to go that way, and G goes from Y to Y prime. So basically, the reason you'll see in a second for the flip-de-doo is that is because of the contravariance of putting Hom in the second slot, as we saw above. So somehow this map should play nice, right, with both of the with both of these morphisms, right? If I decided to change x to x prime and y to y prime. So in particular, you could imagine if we fixed y, right? If we fixed y, then I actually have two functors, right? On one hand, I have the functor, the contravariant functor, that would, eat x's and spit out just, right? This is just an example of a particular, here, this is a particular functor, contravariant Hom-functor where I've just fixed this object. And over here, I've got this other Hom-functor. Well, this is a composition of functors, right? So first I plug in f, and then I take the Hom-functor, right? So this is like the composition of f and homming into y, right? So how do I relate functors? Well, I relate functors with natural transformations, right? So there should be really a natural transformation between these functors. But also, right, also there should be a natural transformation between the other pair of functors, right? So I also have this Hom d. So if I imagine that x were fixed and that I wanted to vary y, right? Then I should also have a natural transformation, or maybe going in the other direction, right? Maybe this one should go in the other direction. Going between these two. And so this is now the composition with G. Great. Okay. So let's imagine how this thing should go. And of course, I have a nice big reference picture behind me. So let's see if my drawing skills. I'm going to give you an unnecessary amount of information, and then we're going to collapse it. But I liked writing it out this way just to make sure that everything was compatible. Okay, so we have Hom. I mean the basic goal. Let me say this is, so we've got on one hand we've got a Hom fx y, right? That should be related, right, to Hom fx prime y prime. We got to find some way to relate those things to each other. But I could also go and relate this instead to Hom using the adjunction map gy, and then down here, this should be Hom x prime g y prime. Right? So the goal is to start here and to somehow relate it to here. Well, okay. So let's think about the steps that we take to get there. So we start off with Hom over in the category D, and I have fx and I have y, right? So we could sort of think about the baby steps that we take to get here, maybe down to here, right? So either I could change x prime first, or I could change y prime first. So remember that by the functoriality that we drew above, one way of doing this is by changing the y prime first. And so this is just using the covariant Hom-functor that I wrote previously. So here we'll have pre-composition by the map G, right? So remember, I've chosen some f goes from x prime to x, g goes from y to y prime. Okay, so I've chosen those. Now the other thing I could do first, of course, is I could instead change the x prime first, right? So what's that map going to look like? Well, remember that I have, right? So first I have f going here. So then that means that my f of f goes from f of x prime to f of x. But then now that gets flipped around, right? Because what I'm going to do next is I'm going to apply the contravariant Hom-functor. So that means when I go Hom fx prime y, the map is now going to go in the other direction. I'm going to get Hom f of x prime, x y, right? And so what's that going to be? That's going to be post-composition with f of f. So I scroll down, and that's what I'm going to put here is post-composition with f of f. Okay, and so finally, I mean, both of these things should end up with f of x prime, y prime. Okay. But now these, I mean, these maps are already set about, right? So it's just going to be these same maps here. So I could go other way around, and that's kind of oh, did I put sorry, this G I think is post composition. That's me forgetting stuff. My pen not working? Is the battery dying? Oh yeah. Well, that's very annoying to have happen mid-video for my pen to start sucking. Right. So sorry, we want for the covariant Hom-functor, we want post composition. Right. So sorry. This should be f of f. This should be post composing with G. This should be post composing with G. This should be f of f. Right. So, well, actually, this whole square was kind of useless, and that's the right, because all this really says is just that composition of morphisms is associative, but we already knew that from the fact that we were in a category. So our one other option, I'm going to draw one more useless diagram and then erase it. But our other option then is now we've got these maps, you know, theta xy that should relate things to Hom in C of x gy, right? So I've got a map there. I should have, this will be theta x y prime C x g of y prime. And now, okay, I need some way to relate these two. But by the way, I'm also going to have a couple other maps. It's going to be, you know, this theta x prime y, and down here will be theta x prime y prime, right? And so let me just draw the rest of my Hom sets in. So Hom C x prime g y, and this will be, ooh, I should not have put that color there. That'll be clashing. Hom C x prime g of y prime. Okay. This really is unnecessarily complicated. But I claim, so maybe I'll just do the answer and skip ahead. So what are all the maps that we're going to get here? So I claim that this map should be given by post composition by f, as will this map. And this map will be given by pre-composition of G of G, and this map will be given by pre-composition of G of G. So you're really just going through and tracking through the, what clearly happens. And so you'll see this dark blue square that commutes again just by the commutativity of induction. So really, any of the real content of this comes down to the top and the sides, right? So actually, what I claim is, because all of these other maps, it doesn't matter which way you go around. The real content of all of this comes down to a much simpler diagram. So that is Hom f x y, and we could go. Let me write this as Hom. So I suppose I should specify my category. That's in D. This will be also in D. And so we can just package up changing the X and Y to X prime and Y prime all in one fell swoop. So this will be X, G, Y, and this will be Hom C, X prime, G of Y prime. And now, basically, just because I insured with this whole useless cube, because I insured slash because of the commutativity of or the associativity of morphisms, it is actually unambiguous to write this as post-composition by f of f and pre-composition by g. So it doesn't matter which one you do first. Same thing down here, post-composition by f versus pre-composition by g of g. So either way, it's literally the same map. And of course, here are so this is theta x, just theta x, y. And down here is theta x prime, y prime. Okay, so this diagram should commute, right? That's what it means for all of these choices of maps to be compatible. And there we have it. That's basically it. I guess this whole, that's been a whole long, complicated thing. I guess the last thing I should tell you is the connection between this bijection condition. So maybe I should just make that last part clear. So remember, so that's the naturality part of it. But how do we relate? I gave you this this unit and co-unit that should give us specifically. So whatever these thetas of x, y's are, right? What relationship does that have with the unit and co-unit? Just to be explicit. Well, actually, I already said that part at the beginning of the video, didn't I? I did. So what a strange place to end. I'll just reiterate maybe up here we used the well, I guess I gave it in the particular case of the sheaf, right? But we use these diagrams to construct the map, right? This is the unit and co-unit diagram. So this is all set up for next time. We're going to talk very abstractly about limits, and I wanted to set up this unit co-unit stuff so that I could prove, or maybe not even prove, but just maybe give you the tools to prove why some such thing as an adjunction and define limits from there. So that'll probably take a whole abstraction next video of limits, and then hopefully the video after that we'll come back down to earth and talk about sheaves and stocks as limits once more. So stay tuned for all of that.